we are doing that when the current is flowing through a circular coil. So we have a circular coil, right? And this is the polarity of the battery. Now traditionally, conventionally, current flows from positive to negative. So the side which is facing towards you, right, that is showing clockwise direction of the flow of current. And the side of this loop which is towards the wall, that is on the other side of the blackboard, is now north pole and this is now south pole. Okay. Now it is like this, but so you can show here that the field lines are merging inside, okay, because this is south pole, right? Now what happens when we change the polarity of the battery and the positive side now becomes negative and negative side we now change to positive, right? Now the current is flowing from this side to this side. You can easily see that it is anti-clockwise. So the end which is facing you is anti-clockwise, the end which is away from you is clockwise. So this is the north and the face which is behind is the south pole. Okay, this is north and that is south. So a circular loop or a circular coil which is carrying current behaves exactly like a permanent magnet, which I discussed with you in the previous video, right? So it is a permanent, behaving like a permanent magnet. It is having two poles. If we suspend it freely, it will direct towards north and south, geographical north, geographical south. Okay. Now what happens if you open this loop? That is, you have now straightened the loop. Now this is the loop. Okay. Now the current is flowing in this direction. Okay. Now you see it is having magnetic field. It is having magnetic intensity, which we denote by B, which is vector. But it doesn't have the polarity like a loop or a permanent bar magnet. There are not the two poles which are present there. It is having, a magnetic field which is in the form of concentric rings. And this was proved experimentally, and the radius is changing, but the circles are concentric. So how it was proved? It was proved like this, that if you have a surface, okay, and you have a straight current carrying conductor which is connected to the battery. Now positive, negative, so flow of current is in this direction. Okay. If you sprinkle some iron fillings, you find that you get concentric circles over here. So these concentric circles are actually the magnetic field lines. Now how to find the direction of this field line? This is done by right hand thumb rule. Now what is right hand thumb rule? Let us think that this is a current carrying conductor, just like this, and you see the current direction is from top to bottom. So you have to hold the conductor in the right hand such that the thumb points in the direction of current. Then your fingers wrap around the conductor in the direction of magnetic field. Now this is, you see, which direction is this? Anti-clockwise. Okay. So if you keep a magnetic compass anywhere, so it will show like this. You see, the magnetic field lines are shown in the form of concentric rings. So a straight current carrying conductor is having magnetic field, but it doesn't have polarity, it doesn't have two poles. Its magnetic field is in the form of concentric circles of different radius. Okay. Now, if we say this is the field and this is the radius, right? So if the needle is kept here at point 1 and you note the deflection of the needle, then you keep needle at point 2. Which needle I am talking about? Compass needle, which is nothing but a very small and light magnet. And then you keep at number 3, you will find the deflection of the needle is more when it is closer to the conductor, right? It means the intensity of magnetic field is inversely proportional to the radius, okay? And then the length of conductor. If this wire is of this length and another wire is of this length, then the magnetic field intensity is directly proportional to the length. It is also directly proportional to the amount of current. So, what will be the force? Though you can say force is equal to will, where we neglect the constant, proportionality constant, right? So this is the magnetic field around a straight current carrying conductor. The magnetic force increases with increase in length, increase in the amount of current passing through the conductor, right? But the influence of the magnetic field through a straight conductor is inversely proportional to the radius of the rings which are around the straight current carrying conductor. So I hope you have understood. Thank you so much.